Okay, seems to be all working. Okay, so as I promised last time, I'm gonna do a little bit of a side tour, by giving a bit of background, without all the many details, but a bit of background on some motivations that are coming from theoretical physics. And we'll see that a lot of things that we have already seen in the previous classes, previous lectures, will kind of show up again in this other context in a very similar form. And I also want to say a few things which have not appeared yet, but that will serve as a motivation for why I'm going to present things in a certain way, in the following lectures. So the context in physics, as I was saying at the end of last time, the context in physics that has a kind of similar structure to the one that we have been discussing is perturbative quantum field theory. So that, of course, quantum field theory is a really huge subject, and there's a lot of different angles in which one can think about it, and which one can also think about the mathematical structures behind it. But essentially, at the level of actually doing calculations in quantum field theory, it often boils down to having a certain perturbative expansion where the calculations are done order by order in a certain perturbation series, which is a formal series, and in powers of the quantization parameter h bar, and the powers depend on a certain grading of combinatorial objects. The combinatorial objects are graphs. The structure of these graphs is determined, as I will say a couple of words about it, is determined by which physical theory you're looking at. And the way that the structure of the graph is representing some specific terms of interaction in the order expansion. A kind of heuristic way of thinking about what a graph represents is that you have certain incoming momenta and certain outgoing momenta with some conservation law that whatever flows in also has to flow out. And but in between, there's some interaction between various kinds of fields and particles. The vertices of the graph represents interactions that can happen. If you can have a certain number of particles of a certain number of a certain type that come together, and another number of particles of some possibly other type that go out of these interaction vertex. So the valences of the vertices are the interaction terms that you have available in your theory. And the internal lines of the graph are products of these interactions that appear and disappear between interactions. And in the end, what you see is only what flows out of the entire structure. So this is like the heuristic meaning of this combinatorial structure. And one of the main difficulties that one encounters in physics in doing this kind of calculations is that the way that each of these combinatorial structures contribute to the thing you're trying to compute is through an integration over all the momenta that are associated to internal lines of the graph, which are the ones that eventually have to disappear. So you're integrating over them, and you're left with something that only depends on what flows in and what flows out. And unfortunately, most of the time, when you integrate over these momenta, you get a divergent integral. And these divergences have to be cured. That's been one of the main theoretical problems in quantum field theory for a long time, and one needs a kind of consistent extraction of finite values from these divergences. You can think of as a consistent assignment of meaningful physical values that are compatible over substructures, and this is called the renormalization problem in quantum field theory. So, here is like some starting to try to build a little bit of parallel between this story in physics and what we have seen so far. So in quantum field theory, we have a certain generative process of combinatorial structures, which builds the Feynman graphs order by order in the perturbative expansion. And this process has two different ways in which you can describe it. One of them is really in terms of formal languages. It's a different class of formal languages than the ones that are we've seen, like context-free grammars, context-sensitive grammars. These are called graph grammars. I'll say a bit about them so that we see that the parallel with the theory of formal languages that one can have in this setting. But there's another way to describe this combinatorial structure of Feynman graph, which is in terms of a Hopf algebra. And this is the Kramer Hopf algebra of Feynman graphs. So for each assigned fixed quantum field theory, you have a corresponding Hopf algebra that organizes the combinatorics of the Feynman graph of that particular theory. And so you can give these two different descriptions of how you build Feynman graph or in increasing order of complexity. But in a sense, one can see that the Hopf algebra description with respect to the formal language description is, in a sense, more useful. And one of the reasons why it is more useful is because it is directly related to this problem of extracting finite values from the divergent integrals. And the idea is that the way that one describes this consistent extraction of finite values in normalization is as a form of factorization for characters of the Hopf algebra, where you kind of introduce a factorization of characters so that one side of the factorization will give you the actual meaningful values where the divergences no longer occur, and the other side throws away, extracts the divergences that you want to remove, and in particular, it produces what physicists call the counter terms. So what you have to correct the action by so that you implement the renormalization directly in the calculation. Yeah. So this idea that the Hopf algebra structure is closely related to this problem of meaningful assignments of values, consistent with substructure is exactly what we want to use, to start it after I finish this part. I'll be introducing what we propose as a model for the syntax semantic interface, and will be somehow mimicking what is happening in this situation for this renormalization problem in quantum field theory. There's another aspect that I have mentioned already, which is the fact that the generative process itself can be described in terms of a fixed point equation, which is a Dyson-Schwinger equation. And in quantum field theory, this combinatorial form of the Dyson-Schwinger equation is a way of describing how to implement order by order the least action principle of classical physics in this quantum setting. So this also has a direct analog of the same structure occurring in the quantum field theory context. So I'm roughly going to be illustrating a few of these things right now. So one of them would be how one can think in terms of formal languages in the physics setting, and that get sort of parallels the older formulation of generative linguistics. And the comparison between that and the Hopf algebra formulation, where the Hopf algebra, also the Hopf algebra of Feynman graphs takes care of the composition and decomposition of Feynman integrals, different order in the expansion. And the other thing that I'll say a few more words about is this fixed point type problem that are the combinatorial Dyson-Schwinger equations, for which we have seen an analog in the previous lectures. So the idea, as I was saying, yeah, and like I said, one other thing that I want to mention briefly is the fact that there's kind of an intermediate step between the story of quantum field theory in theoretical physics and this parallel story in generative linguistics that I talked about. So this Hopf algebra formulation of renormalization is dating to around 1999, 2000, and a few years after that, where it was completely formalized in these terms, the recursive BPHZ renormalization procedure of theoretical physics. And a few years later, in 2009, Manin proposed this idea of doing a similar kind of structure with Hopf algebras and factorization in a setting that's different from quantum field theory, and which is in the theory of computation, where in a sense you also have infinities. So you have the infinities like the halting problem. You don't know if your running time library is finite or not. And you have undecidable problems which have exactly these characteristics that they are like the infinities in the theory of computation. And it's it's also the case that sometimes you have some function that is not necessarily a computable function, but it's not so it can be described. I'll say a few more words in a bit, but it can be described in such a way that the being computable or non-computable depends on a certain domain, where so your algorithm that you try to use to compute such a function will terminate if you are in the domain, and will not terminate if you are not in the domain. But since you don't know, because the ultimate problem is unsolvable, whether it terminates or not, then this makes the problem undecidable. But the fact is that very often in a problem that's undecidable, you can extract sub-functions that are decidable. And so you can kind of localize where the undecidability is, what the undecidability is caused by. And so this is, in a sense, is like localizing where the divergences are caused by in quantum field theory. And so there's like an analogous story. And so in some sense, this is like the missing link in the in the evolutionary step. The linguistic side is, in a sense, a next step in passing from the quantum field theory, to this theory of computation, and then to generative linguistics, which is a way of thinking of language itself as a kind of computational process. So this overall suggests this strategy, which is the one that I will be following then, of really interpreting the semantic parsing of syntactic objects as a kind of extraction of finite values in this across, with consistency across substructures. Okay, so let me just give a sort of hand-waving description of what happens in physics. So when you're doing perturbative quantum field theory, and I'm just assuming that my fields are just scalar fields, so I don't add more complicated things, whatever, sections of bundles, spinors, gauge fields, and so on. There's a lot more. It can get a lot more complicated, but you see already all the structure if you just think that there is like a single scalar field. So that's kind of the simplest thing that you can do. So if you have such a quantum field theory, it means that you're specifying an action functional. So you have a certain Lagrangian density, which usually has a kinetic term, and the signs depend on whether you are in Lorentzian or Euclidean signature. It doesn't matter for what I've done, level of generality that I'm keeping here, but you have like a kinetic term, which is basically the free field with no interaction, and then you have some other terms, which are usually polynomial in the field, which are the self-interaction of the field with itself. So it could be a phi cube theory. It means that it has a cubic interaction. It's a phi 4 theory. It has a degree 4 interaction. It could be a combination of phi 3, phi 4, that has several kind of possible interaction terms. And the idea is that you can incorporate the quantum corrections into the action by an expansion where the terms of the expansions are labeled by a collection of graphs. And this collection of graphs depends on the actual form of this Lagrangian, in particular on what kind of powers you have here. Because as I said, if I have a cubic term, a cubic interaction, I can think of it as being 3 copies of my fields that are coming together and interacting. So I can think of it as generating vertices of valence 3 in my Feynman graph. If I have a phi 4, I would, if I have a phi 3 and a phi 4, I expect that my graph will have some vertices of degree 3 and valence 3 and some vertices of valence 4 and so on. Okay.
S effective here is for the whole S, right? The expansion is for the full S action.
Yeah, that's right. Yeah, that's right. But the thing is that you have, you always have like a term which is your free action, and then you're putting quantum correction terms on the rest of the interaction by counter terms that correct the coupling cost. Okay, so as I said, so the formula for doing this kind of renormalization procedure had been around in the quantum field theory literature, I think since the 60s or something like this. And it is the most complete formulation. But the actual, an actual complete understanding of how this normalization procedure works and what this formula actually mean, what you are actually doing, was in fact something that was done about 20 years ago. And so the idea, if one tries to actually check in a more precise way what is going on in this renormalization story. So first of all, there are two steps that are actually separate from each other. One of them is that you first regularize these divergent integrals. What it means to regularize that is something like this. So there's an integral you're trying to compute, and it diverges. But you can fit this integral inside a family that depends on some parameters. And you can do it, if you can do it in such a way that the divergence of that integral corresponds to the fact that your function of whatever parameters you're introducing happen to have a singularity, like a pole at some particular value of the parameters, but is well defined elsewhere, then you can attribute the divergence, the integral, to the fact that you were hitting a pole of a function. And so this means that if you move away from that pole, you get something that's not divergent. Except that, of course, now you get something that depends on whatever auxiliary parameter you have introduced to make this deformation of your function. And in the end of the day, you want to extract something that is not dependent on additional parameters. So at this point, this is where you cannot just regularize your integral, because you need to then do something that will get you rid of these additional parameters that you have introduced. And so the other step, which is the renormalization, is that once you've chosen how to regularize these integrals, then you want something that will subtract away a divergent part. Like, for example, if you have a function that has a pole, you want to subtract away the polar part of this function and get something that now you can evaluate back at the point where you had the problem before, and now it's going to give you something that has a finite value. And this is, however, where the combinatorial structure comes in, because you're trying to do this subtraction of polar part order by order in your expansion. And the divergences, the pole structure, when you're looking at the graph, is coming from several things. It could come from several subgraphs. It can come from the entire graph, but not from some graphs. It can come from some subgraphs, and so on. And so, in particular, if you have divergences that are coming from subgraphs, you have already encountered them at earlier stages in your normalization procedure, because these are going to be graphs of lower order. So you have already done the renormalization at lower order, which means that the way you do it at higher order has to take into account how you have already renormalized the lower orders. So you cannot just subtract the pole of the entire thing that you see, because that's going to give you some inconsistency, which sometimes mean that you don't get good counter terms that you can introduce in the action to correct for the divergences. And so you want to be able to make sure that you do this subtraction in a consistent way across all the subdivergences that you can encounter in a given graph. And so this is where the combinatorial structure is important to keep in mind. And there is another point that there are usually several different regularizations that one can do for a given Feynman integral. There are things like dimensional regularization, cutoff regularization, zeta function regularization. There's a whole like industry of regularization schemes that you can use for Feynman diagram. But at the end of the day, the physical values that you extract have to be what they are. I mean, they have to be something that is measurable in some experiments. After all, quantum field theory is the one physical theory that is verified to the highest order of precision that ever existed. So, these things are too much. So there is also this fact that you have to have some kind of way to move between different regularization procedures so that you ensure some consistency when you do this renormalization process. Okay, so this is sort of the main setup of how things happen in this context. And the combinatorics, as I was saying, is encoded. So I'll show later how one can also encode it in terms of formal languages, but in the renormalization theory, it is encoded in terms of a Hopf algebra. The Hopf algebra is generated by the Feynman graphs of the theory. So there's some subtleties here in the sense that usually when one looks at the Feynman integrals theory, the only strict requirement that you have is the fact that the valences of the vertices have to be corresponding to the powers that you have in the interaction terms in the Lagrange. So only certain valences are allowed. But other than that, you can join the edges in a priori whatever way you want. This means that, for example, you're going to have graphs that have several connected components because it can happen that your edges match in such a way that you create more than one component. Well, these are sort of redundant because when you compute the Feynman integrals, you're integrating over the momentum variables that are associated to the internal edges of the graph, and each vertex has a conservation law because everything that flows in has to flow out. The momentum is conserved in all of these interactions. So, but this in particular means that if you have different components, the momentum variables in one component and the momentum variables in another component are completely independent. There's no momentum conservation that involves both of them at the same time. And so your integral factors as a product because it's completely independent set of variables. And this means that you can always assume that your graphs are connected and that a disjoint union of connected graphs goes to a product of the corresponding Feynman integrals. So you have this kind of multiplicative properties of your Feynman integrals.
Sorry, is each connected component, are you saying one is a phi3 term, one is a phi4 term? So they are independent, or are you saying that for each term you're looking at a perturbative expansion and each order is independent?
Yeah, so suppose that you have a Lagrange that has both a phi cube and a phi 4 term, right? So it means that your Feynman graphs can have vertices that are either of valence 3 and of valence 4. So you can start like with a bunch of vertices. So say you are whatever at order n, you're in loop order, but so you're gonna have whatever number of vertices allows you for that fixed loop order. But then, so you think of the corollas, right? The trivalent vertices and the 4-valent vertices, and I start to match edges to make in all possible ways to make my internal edges, and some are left as external edges that give you the incoming and outgoing momenta. And you will have things where you're going to have different components. Each of these components can have vertices of valence 3 and 4 because each of them is a Feynman graph. So as long as it doesn't have vertices of valence 5, say, it's okay. As long as the vertices, it could be that some component might have only vertices of valence 3. Some might have mix of the two kinds of vertices, but all of these are allowed. But the thing is that I don't have to count all possible graphs. I just need to count the connected ones because the other ones are just the product. If I know how to compute the integral for a connected component, then for a graph that have several components, it's just the product of those. So I can really think about just the connected graph. And there's a further simplification of the combinatorics that is known in physics, which is these 1-pi graphs. And these are actually graphs where they cannot be disconnected by cutting a single edge. So you're like, for example, if I have a chain of like one edge, something, one edge, something, well, this would not be one particle irreducible because I can cut a single edge and disconnect it. And the point is that there's again a similar argument. You can, if you know how to compute the ones that are one particle irreducible, you can compute all the other ones again as a product with a single propagator that connects it. So the others are determined. So this means that, okay, you can take as generators of this Hopf algebra, these connected and one particle irreducible Feynman graphs of your theory. And as an algebra, it's just a polynomial algebra over these, which means that you take basically this joint union of these and the corresponding integral that you compute will be a product over this joint union. So as an algebra, it's just the commutative algebra generated by these graphs. And the degree of a graph is the number of loops, because that's the order of the expansion that you want to keep track of. So the trees which are the degree 0 part, which will just don't correspond to the semi-classical limit of theory, you don't consider them here. You just consider things that have at least one loop. And the coproduct, well, the coproduct is designed exactly for the fact that when you need to check for the consistency of renormalization, you need to check what happens on substructures. So you need to be able to extract substructure and consider separately a subgraph and what happens with what you're left. So when you remove that subgraph. So the coproduct is given by all the possible ways in which you can extract the subgraph and take a quotient graph. The quotient graph just means that your subgraph gets contracted to a single vertex. And so of course, you have to make sure, right, that this is still a Feynman graph of the theory, which means that that vertex has to be of the right valence that's allowed. So you want to extract. So there's a certain set of subgraphs that you extract. The subgraphs that you extract are exactly the ones that have the property that when you shrink that subgraph to a single vertex, this has the right valence to still be in the same quantum field theory that you're looking at. So, and this does satisfy the co-associativity property, and the product is just the disjoint union of graph that gives you all the graphs that have multiple connected components starting from the connected ones. So the product is again just a disjoint union, as in the case of trees that we were looking at, and the coproduct extracts substructure and takes quotient structures. And again, this algebra is graded connected and commutative. So it has again this property that we have seen, that the antipode exists. So the bialgebra determines the Hopf algebra structure. The antipode exists and is defined inductively in terms of the lower degree terms of the coproduct. So
can you remind again, V gamma was the set of all subtrees subgraphs including the original graph, or not?
No, so the original graph goes into the primitive part, right? So when you extract everything and you're left with nothing, or you extract nothing and you're left with everything. These are like proper subgraphs. And the condition that you have to put on which subgraph is that this has a vertex of valence, whatever is allowed in the quantum field theory. So if I am in phi cube, I can only extract subgraphs so that if I contract that subgraph to a single edge, so a single vertex, that vertex has valence 3. If I contract something for which it has some other valence that's not an interaction term in my original Lagrangian, then I don't want to consider those as terms on this coproduct. Because I really want to be able to separately look at whether my divergences are located here or here. So these have to be Feynman graphs of my theory. So I'm kind of, this plays the same role as you know, the way we've seen the coproduct playing a role in this definition of merge in the linguistic setting, because you want to be able to extract substructures and look separately at a substructure and what is left. And again, you know, here you have the same problem that we have seen there, like what is left is or is not part of the same structure, right? Is it no? And so here the condition for ensure that this what you have left is still part of the same theory is a condition on the valence of vertices. So that tells you which subgraph you can extract.
But if before you contract it was higher than 3, and say 3 was the maximum interaction term in your theory, before you contract, why would it be higher than 3?
Yeah, I mean, you see, the thing is, I could have, yeah, when I take a subgraph, it means like I look at a certain number of vertices, right? And that form my subgraph. And these have edges that are connecting them to other parts of the graph. Like, for example, like if I have this graph, right, two and one edge in between, these two vertices have valence 3. But if I contract this edge, I get the valence 4 vertex.
Yeah.
So unless my original Lagrangian also has a phi-4 term, I cannot take this subgraph, right? If it only has a phi-cube term, then I should not extract this, because it would give me a term that is no longer part of the same theory. Right?
So it can be a certain valence in the original thing, but you can contract it to get a higher valence, and you don't want to get
That's right. You don't want to do that, right? If you contract something that is going to give you a higher valence that is not part of the list that you have. Yeah. Okay, so but this still works. So even if we put this restriction, it does give you a coproduct that is co-associative and is compatible with the product and has all the structures that you want. So,
but you haven't written it down here. You haven't written down this constraint here in this coproduct.
Yeah, that's it. So I mean, the thing I'm saying is that if you define the coproduct like this with this condition, right? So this defines which set you're taking out the subgraph from. And then so this is saying that, you know, each theory has a slightly different coproduct, right? Because the set of terms that you are allowed to extract depends on the theory, but all of them have all the properties that are required for being a Hopf algebra.
And they have the same product.
And they have the same product. Okay. That's right. The product is always the disjoint union, and for all of them. That's another example of the fact that the coproduct is more subtle than the product here. The product is the same for all of them. The coproduct is not just decomposing according to the product. There's something more subtle, and this other part is now theory dependent, while the product is not.
So which one is more informative about the divergences? It will be just the coproduct, right? Yeah,
that's right. So the coproduct is the one that is actually involved in the renormalization structure. The product is really just saying, this fact that your Feynman rule is, independent on different components. So that is a product. I mean, an integral over a set of independent variables is the product of the integrals. So there's two sets of variables. That's the only thing that the structure of the product is keeping track of. Okay, so now this is like the combinatorial part. The combinatorics of Feynman graphs is organized according to this Hopf algebra. Now the regularization part. So as I said, you want to turn a divergent integral into something that depends on a variable, and that happens to be divergent because you were hitting a pole in that variable. So you need some place where your regularized integral take values, which has an operation, and this operation should be something like a projection on the divergent part. So you want to have some kind of projection that allows you to separate the divergent part from the convergent part. So the prototype model for such a thing is the ring of Laurent series in one variable. So you have a power series and polynomials in the inverse. So this is Laurent series. And the projection on the polar part. So if you write the series, the sum a, k, z to the k starts at sum minus n, goes to infinity. This projects onto the part sum from minus n to 0 to minus 1. So everything that has negative powers of z. And then the complementary projection is on something that is actually a power series, so it does not have divergences. Okay. And so, of course, it's easy to see that if I project like this, so if I take a power series and I separate it out into the thing that only contains negative powers of z and the thing that only contains non-negative powers of z, this operation is not compatible with taking the product of series. So if you take the product of series, the exponents combine, right? So of course, you will get terms that go into the different places, the two different pieces of the decomposition that mix. So this projection is not, and is a linear map. So it's a map of vector spaces, but it's not a ring homomorphism. However, it has something that's better than just being, it's something that's in between. So it's better than being just a linear map. It's not as good as being a map of rings. If you look at how it fails to be a map of rings, so if you take the product of the projections onto the polar part, it's not the same as the projection of the product, but it's related to it by an identity, which is funnily looks a bit like an integration by part type of identity, right? And there's a number here, and in this case, this number is actually -1. So this identity is called a Rota-Baxter algebra of weight -1. In general, the Rota-Baxter algebra of weight lambda is something where we'll have some number lambda there. And if lambda is equal to 0, integration by parts is actually a Rota-Baxter operator of degree 0. So that's why it looks like integration by parts, because the integration by parts is also a Rota-Baxter operator. And why is this identity interesting? It's because, you see, it just tells you something that if you take, so T projects onto the polar part. So if I take the polar part of a product, even though it's not the same thing as the product of the polar parts, it is something that's always in the range of T, because it's a combination of three terms, each of which is T of something. Or rather, it's better reading it like this, right? If I take a product of two polar parts, okay, the product of two polar parts is a sum of things that are T of something. So it's in the subspace. So this is saying that these projections are not ring homomorphism, but their range is a subalgebra. It's not just a subvector space. So it's a way of decomposing a vector space that happens to also be an algebra into two vector spaces by a projection. And the projection itself is not compatible with the algebra structure, but each of the subvector spaces remains an algebra. So it's kind of fairly strong condition, as opposed to just being a linear map or just being a projection in the linear sense.
But it remains a commutative unit algebra?
It remains a commutative algebra, a commutative associative algebra. And exactly because this property is just saying that if you take the product is just the product that's induced from the overall algebra, so it is still commutative and associative because it is on the whole space, and this is just ensuring that the images stay within the same subspace. So if you take a product of two things that are in the subspace, the range of the projection is still in the range of the projection. So the range of the projection is actually a subalgebra, and so the same for the complementary projection.
But I don't see how it's obviously closed, and you can say that it's an algebra, it's a subalgebra.
Well, because it is closed under the vector space structure because T is linear, right? And
it's linear, okay.
Yeah, T is assumed to be linear. It's a linear projection. The thing is that it's not an algebra homomorphism, so a priori it's not closed under multiplication. But the fact is that it's also closed under multiplication because this identity is enough to ensure that. Yeah. Okay, so then what is the regularization? So a regularized Feynman rule, right? This is in more general, you can say an abstract regularized Feynman rule is just a morphism of commutative algebras from the Hopf algebra of Feynman graphs to some algebra, commutative associative algebra, R. So what this is saying very little. It's just saying that the only property that you are preserving is the fact that if I have a disconnected Feynman graph, then its integral is a product over the two components. This is what being a morphism of algebra is saying. I mean, the linear part, I just extend everything by linearity because my graphs are the basis. So if I define what it does on the basis, then I extend it by linearity. So the linear part is like a triviality in the sense that I'm defining how it's defined on the basis. But the commutative algebra is just this multiplicative property. And this is simply this fact that independent components go to the product of the corresponding values. So this is saying very little. And in particular, this such a map is completely oblivious to the fact that H also has a coproduct. It's not just an algebra. And R also has this Rota-Baxter type projection. It's not just an algebra. But phi doesn't see any of those. Phi is just seeing the product structure of the algebra, which is this completely trivial product structure, which is just putting it together by the disjoint union in the case of the graph.
So they are not both associative and commutative, right?
Yeah, so both are associative and commutative. Yeah. So this is a morphism of commutative algebra. By commutative algebra, I give for granted the associative part. Yeah. Okay, so the
sorry, the reason I asked that is because you just defined phi as a commutative algebra homomorphism. Yeah. And you're saying it's going from something to something, and one thing has a co-product, another has.
That's right. But as I said, the fact that I'm saying is a commutative algebra homomorphism, it means that phi knows nothing about these other structures.
But what I was going to ask was, why can't you just say that H also has this kind of identity projection, because it's just the same type of algebra as R?
No, it's not. I mean, H is a Hopf algebra. It doesn't have any Rota-Baxter structure. R has a Rota-Baxter operator. It has no Hopf algebra structure. So these are like the only thing they have in common is that both of them are commutative algebras.
Okay.
Yeah, that's actually it's a very interesting point in the sense that, especially I'll come back to this when I'm going to talk about the linguistic counterpart, because for a long time, a lot of models of semantics that people have tried to do that are compatible with generative linguistics, they've tried to mimic on the semantic side all the structure that you have on the syntax side. And the point is that this is not necessary. And this is exactly where you see that it's not necessary. Because these two objects are of a very different nature. The Hopf algebra structure is entirely on the combinatorial side, which is the one that takes care of the combinatorics of the Feynman graphs. This side is only where your integrals take values. And the thing is that this by itself does not have to know anything about this Hopf algebra structure. In general, it's never a Hopf algebra, this thing. And what you need on this side is this kind of projection that allows you to separate out divergences and non-divergences. Like Laurent series. You're not trying to put a coproduct on Laurent series. All you're trying to do is like have what is good about Laurent series is that you have a polynomial in Z inverse and a series in Z, and you can separate out these two. And the point is that the regularized Feynman integral sees only what these two things have in common, which is the commutative algebra structure, and it doesn't have to see anything else. The rest you're going to use to construct the renormalization of this character. But the character itself that you start with, so this is the regularization part. That's why I'm saying the regularization and renormalization are really two different steps. Regularization is only seeing the commutative algebra structure, and renormalization is actually seeing the co-algebra structure on one side and the Rotha-Baxter algebra structure on the other side. And then you of course you need both steps, to be able to do this renormalization construction, but these two steps have a kind of different nature from each other. And so the characters of a Hopf algebra in general are exactly these things. And so the terminology here, I think, is pretty bad, because people call these characters of the Hopf algebra, but they are really characters of the underlying commutative algebra, because they're not depending on the co-algebra structure. It's just that the terminology in use is that people call these characters of the Hopf algebra, but they are homomorphism of commutative algebras from H to some pi. Okay. So
are they satisfying any axioms? Like, are they a group of homomorphisms?
Right. So of course, a priori, this is a set, right? Because it's the R points of the scheme that is dual, the affine scheme that is dual to H as a commutative algebra. But in fact, of course, H actually has a co-algebra structure, and so this is a group. It's not just a set. The group structure is coming from the co-algebra structure. And so this is the R points of the affine group scheme dual to the commutative Hopf algebra. Okay, so now is where you actually start to use the fact that you have also the coproduct and you have also this Rotha-Baxter structure. Indeed, the coproduct enters exactly because of this observation that this is not a set, but is in fact a group. So you can take two of these characters and you can multiply them together. And what it means to multiply them together is this thing that I've already discussed before, that the product of two such characters is just, you take the co-product of what you apply them to, and then you apply the first one to the left side of the coproduct and the second one to the right side of the coproduct. And so this coproduct is a sum of terms, like the primitive part 1 tensor x or x tensor 1 will just give you the sum phi1 of x plus phi2 of x. And then the other terms will give you correction terms that have products of phi1 of x prime and phi2 of x. Okay, so this is the product. And in particular, because it's not just a co-algebra, a bi-algebra, but it also has an antipode. The antipode also gives you an inverse for this character. So it is a group, not just a semi-group. And so in particular, you can look for a factorization of phi into two pieces, one of which you write as phi minus composed with s, which would be like phi minus inverse by times phi plus, right? It's a multiplicative decomposition of phi. And you want to decompose it in such a way that one part, so the coproduct tells you that you can take this product, right? But now I'm using also the Rotha-Baxter operation on the target. The Rotha-Baxter operation on the target tells me that R decomposes into two pieces, R plus and R minus, which are respectively the part that has or does not have divergences. And so I want my phi to split multiplicatively into two parts. One of them, so these parts are still morphism of algebras. And this is where I want to use the fact that this R plus and R minus are algebras, they're not just vector spaces. So I need the Rothenbuxter identity for that. And I want these two parts of the decomposition to land in these two parts of the algebra. So one will land only in R plus and one will land only in R minus. Okay.
Phi
So-
minus of x is in R minus.
Yes, sorry, phi minus will land in R minus, phi plus will land in R plus. And this is the way that you split into, regular parts and part that takes away the divergences. And so you want to show this, right? You want to show that this decomposition exists. And also, up to a normalization factor is actually unique. It's not, but that you can always do this decomposition. And the way that one shows that it exists is again by an inductive argument, which is based on the fact that the coproduct has terms of lower order. And so you can inductively make an argument, like you define the antipode inductively, the same kind of inductive formula that you use to define the antipode, you use to define this decomposition. So what you do is you assume that you have already defined what this negative part is on the lower order terms, and then you kind of correct the part that you're looking at, which is this one. You correct it by how you have already extracted, what you have already extracted for all the smaller terms that occur in the coproduct. These are all the substructures, because the left side of the coproduct extracts substructures. The right side of the coproduct takes quotients. So this is like your subdivergences. The phi minus is the divergent part, X prime is the substructure. So this takes into account what were all the divergences that were coming from substructure that you have already encountered before. And this was the corresponding integral on what is left when you have extracted a substructure. And the thing is that now you don't just do this. So you don't just take the polar part of phi of x. This would be like if you didn't have to worry about substructures, where you would just take every graph, look at the corresponding Laurent series, and just throw away the polar part. So this would just be doing this. Or this would be taking the polar part, and this would be throwing away the polar part at the other side. But if you didn't have to worry about consistency over substructures, you could just do this, and this would be enough. But if you do this, you get inconsistencies, and then you don't get like well-defined physical values that you extract at the end of the day. In order to do it consistently, you have to take a sort of like an inclusion-exclusion, where you keep looking at the previous terms and you arrange them so that in the end, everything is counted correctly, right? And so if you do this, then what happens is that this has this property. It has exactly the property that it splits this way. Also, this is the only thing that will have this property that splits it this way, because the antipode itself has a kind of structure like this. And so the fact that you have phi minus composed with the antipode is exactly what corresponds to the fact that phi minus here has all these terms here, because the antipode has all these terms. So when you compose phi minus with the antipode, you necessarily get these terms. But the antipode have this form, right? And so when you compose phi minus with the antipode, you are applying phi minus to all of these things. Okay, so that's why you necessarily get something of this form. And in fact, this is the only way up to a normalization constant is the only way that you can obtain that factorization. So
you could have come up with a formula and adjustments. The only way to do it.
Yeah, that's right. This is the only solution to this equation up to a normalization, up to an overall constant normalization factor. So, and the reason, as I said, the reason why this is the only solution to this equation is because of the form of this recursive way of in which the antipode is constructed.
What's the pseudo induction? How does this Where does this start?
Hmm?
Where does this start? What's the seed of induction? Is it the tree of the apples?
Where the induction starts? Yeah, so I mean, the first term you have is the primitive part of the coproduct. So it's just x tensor 1 plus 1 tensor x. So the first term is this, yeah, this is the part that's coming from the primitive part. And if you only had the primitive part, then it means that you have no subdivergences. This would be just the graph that where you don't have to worry about any subdivergences, and then you just really take the polar parts or the renormalized part of that Laurent series without doing anything else.
Okay, this gives me phi minus x in terms of phi minus of the small one.
Yeah.
So I must start somewhere. What's the smallest?
Yeah, the smallest is the empty set because you have the x tensor empty and empty tensor x.
The empty set has all the indices you want.
Yeah, that's the unit of it's the unit of the algebra. That's where you start. Yeah. Okay. Okay, and so no, the other thing is that then one manifestly sees that the formula that are written in this way actually do match these BPHC renormalization formulae as the way that they were written in the physics literature originally. Okay, so of course, and in the case of where your target R is indeed Laurent series in one variable, then this phi plus is now something which is just a power series. So it has a well-defined value at 0. And this is the actual renormalized value that you want to take. And this is what counts as the divergent part. That's
So sorry, if you step back for a second. So
Yeah.
What has renormalization done? It's just got rid of the divergent part? Or?
That's right. So this literally separates out, right, the divergent part from the convergent part. And now the convergent part you can actually evaluate at the point that previously was a pole. Now it's no longer a pole, so you get an actual finite value. And that is your renormalized value. So here, this is formulated in terms of the Hopf algebra Feynman graphs. There is a relation between the Hopf algebra Feynman graphs and the Hopf algebra rooted trees that I've been discussing before. In this setting, the trees are not necessarily just binary; they have arbitrary valence as trees, and but the coproduct is exactly the same that we have been using, namely the one that makes admissible cuts on the tree, takes on the left side the forest that is falling off when you do this admissible cut, and on the right side whatever is left attached to the root in the original tree. And so the way that this algebra of rooted trees is related to the Feynman graphs is that if I give you a Feynman graph and I want to organize, I mean, with the previous coproduct, I look for subgraphs that I want to extract. And the way that I can think about looking for subgraphs that I can extract is in terms of a tree that organizes how graphs are nested inside larger graphs. So if I look at this Feynman graph here, I know that there's, for example, this subgraph that I can extract, or there's this subgraph that I can extract, for example. And in this case, I can think of them as being these two, and then they both subgraphs of the same graph, but none of them is a subgraph of the other. So I can write a tree that tells me how the subgraphs are organized, which an edge means that one of them is a subgraph of the other, and there's no edge directly between these two means that none of these is a subgraph of the other. Okay. And of course, you can see that these trees don't need to be necessarily binary, because I could have like an additional graph somewhere else, and this could be valence 3 or valence n. That's you have all possible valences of trees. Yeah.
You're only showing depth 1 cube, right? You're showing only depth 1.
That's right. This is an example just, but if I have a larger graph, then I could have, like, for example, I could have, I don't know, another loop here then I would have like an order 2. Now this would have itself another, another structure. Yeah. And so but of course, just the tree itself loses some information because you also want to know what graph was attached to each of these. So in fact, in this formulation, this would be rooted trees with vertices that are labeled by Feynman graphs. And it's just telling you which Feynman graph was the one that you extracted at that point.
Can you remind me what was Bice and Rossi? You've used that notation before for coproduct, right?
Yeah, that's right. So this is like the part, so the notation is just different to remember that one of them is what is attached to the root, to kind of write it as rho C. Remember that's something. This is the part that was attached to the root. So this is always the tree. And this is the part that falls off, right? And this is in general a forest. It's not a tree. Okay, so the passing from this formulation with Hopf algebra of graph to this corresponding formulation of Hopf algebra of trees with labeled by graphs, labeled by Feynman graphs, is actually useful for formulating these combinatorial Dyson-Schwinger equations in quantum field theory. And this was also done in a few years after this formalism of algebra formalism was introduced to describe renormalization. And the basic idea here is that you describe this, so this Dyson-Schwinger equation describe again this generative process of Feynman graphs in a way that it combined together into single fixed point equation. And the point of that is that then when you evaluate your Feynman rule on the resulting entire series, you get this order by order implementation of the sort of action minimizer in the what would be the action minimizer in the classical sense, right? So it's a bit of an argument to show that, but I mean, I just want to focus on the combinatorial structure underlying this rather than on the actual evaluation of the equation of motion, of the quantum equation of motion. And the point of these equations is that the combinatorial structure that describes this fixed point equation that gives the combinatorial Dyson-Schwinger equation is exactly this grafting operation that we have been using also to describe the merge action on workspaces. And in general, they are these operations that take a forest and combines it all together in a single tree by adding a single vertex and attaching all the roots of the trees in the forest to this single vertex. And in general, it depends, because the vertices are labeled here, it depends on a certain label that you put at that vertex. In the cases that we looked at, only the leaves, in the case of merge that we looked at, only the leaves are labeled. And so in that case, you don't care, you have to carry which label you put at the root, but here you don't. And this operation, this grafting operation, satisfies so if you look at how it behaves with respect to the coproduct, so if you do this grafting and then you compute the coproduct, it's the same as, it's not quite the same as first computing the coproduct and then doing the grafting, but there's a relation between them. And this relation is again this kind of co-cycle condition that says that this operation defines a cohomology class in the Hopfian homology of the Hopf algebra. So there's like a nice algebraic structure associated to this operation. And the equation that describes the Dyson-Schwinger equation is coming from, looking at a fixed point equation where you make a formal variable that is a sum of variables in each degree of the Hopf algebra. And then you write an equation where in each degree you apply this grafting operation, and it becomes a an equation in the coefficient that satisfy this fixed point. And it, in general, there's some very general results. I'll try to add some papers to the webpage that give the detail of the general form of solutions for this equation in different settings. And in particular, the solutions of one of these Dyson-Schwinger equations define a Hopf ideal in the Hopf algebra. And so implementing these equations of motion corresponds in the Hopf algebra sense to taking a quotient with respect to this ideal of this Hopf ideal. So that's kind of the algebraic form that the equation of motion, the quantum equations of motion, take in this Hopf algebra formulation of quantum field theory. And I don't want to go much into details on this, but it's just because we have encountered like this most basic form of this Dyson-Schwinger equation, which is just this quadratic equation with this merge operation of this just binary merge operation as the thing that describes the generative process of the syntactic objects, and it's indeed like the simplest case of this family of equations. So another thing that we have seen, that has also a corresponding role in the quantum field theory picture is this dual Hopf algebra and the Lie algebra that's dual to the commutative the connected Hopf algebra. And this again also exists in this quantum field theory setting for the Hopf algebra Feynman graphs. And it has the same structure as the one that we have discussed before, where you have these insertions that happen not like merge at the root, but that happen to insert as some inner part of the tree. And here you do a similar operation on the Feynman graphs. So it's again the same property that I discussed, that you describe a Lie algebra in terms of this pre-Lie structure that corresponds to this insertion operation. And the Lie bracket is an anti-symmetrized pre-Lie structure, so it's an under-symmetrized insertion in this sense. And this pre-Lie identity is the one that ensures that the Jacobi identity for the Lie algebra holds. And so you have and also, as I was saying already, for our setting in the linguistic part, this Lie algebra is really the Lie algebra of primitive elements in the dual of algebra. So meaning that something is a primitive. So this condition here is the primitive condition in the dual of algebra. These are linear maps. And if you want, this is a Lie algebra scheme in the sense that you can take linear maps with values in some commutative algebra, which is not necessarily just the field itself, but in general, you require them to have this property. And if you see what this means, I mean, this is the product, but the product is the coproduct in the dual of algebra. So it's really saying that this is a primitive element with respect to the coproduct, because this is the co-unit, which is the unit in the dual of algebra. So this is really being primitive for the coproduct for the coproduct of the dual of algebra. So it's exactly the same setting that I was describing for these countercyclic movement and late merge in linguistics. And here, what it looks like in terms of Feynman graphs, if this is the coproduct of Feynman graphs, where you extract the subgraphs and take the quotient graph, like you have this kind of example. Like if I take a coproduct of a graph like this, I have the primitive part, and then I can extract one or the other of these triangle graphs. I have two ways of doing this. If I shrink it to a vertex, I get this. So these are the only other extraction of subgraph. And the corresponding Lie algebra structure becomes the insertion of one Feynman graph into another at all the places where you can insert it. Okay? So what that means is that I want to insert, so my graph is going to have a certain number of external edges. So if I want to insert it somewhere, it means that I want to take a vertex in the other graph and I want to replace that vertex with the graph that I'm trying to insert. So it means that the valence of that vertex has to match like the external edges that I have with this graph. And then I place it like in all possible ways there. Okay, so that the external edges are glued to the corolla around the vertex that where I'm trying to do the insertion. So this is like how this pre-Lie like insertion structure works. So this is the thing that I'm trying to insert here. And so I can insert it here. I'm actually thinking in this case that I really have a vertex of valence 2 on each of these edges. So I'm inserting, because this as external structure that is, I have just 2 external edges. So I can insert it only if I have somewhere a vertex of valence 2. So here, no, it doesn't show in the picture, but I'm thinking of that each edge has a vertex of valence 2 in the middle, and so I can insert it in each of them. And if I try to do it the other way around, now this has 3 external edges, so I can only insert it wherever I find a vertex of valence 3. And so there's 2 vertices of valence 3, and so I can insert it either here or here, and in both cases I get this stuff. Okay, so this is how the pre-Lie structure works. It means you search for all the possible ways where you can insert, and you do the insertion in all possible ways where you can insert. So
you don't consider external edges in this kind of. You don't imagine that there is.
Yeah, no, there's an insertion in the interior of the graph. Yes, like for the trees, right? You don't insert when we do this Lie algebra for the Hopf algebra of the rooted trees. You don't insert at the leaves. You insert at the interior. And so the Lie bracket is this symmetrized, anti-symmetrized, insertions that you can do. So in this case, right, you would have a term that takes care of these insertions and the other term that takes care of this. It's the difference between these terms. Okay, so this is the analog of all of the structure that we've seen, right? This is the way that they show up in physics and in the corresponding roles. And as I said, there's a different way to think about the generating Feynman graphs, which is actually more similar to the older way of thinking about generative linguistics in terms of formal languages. And you can do that also with the Feynman graph. There is an extension of the theory of formal languages, which instead of dealing with strings of text or of strings in a given alphabet that are obtained by production rule, you actually deal with graphs. So your terminals are not strings; they are graphs. I mean, if you've seen the movie, this science fiction movie Arrival, which has some interesting linguistic stuff, hidden in the story is the fact that these aliens are speaking in graph grammars. It's sort of cool idea. And so they are speaking some kind of quantum field theory.
That's why they could see through time, right?
But so again, no. I'm just going to tell you briefly something. When you look at quantum field theory from the point of view of these formal languages, the graph grammar, there's 2 things that you observe. So there's a notion of context-free graph grammars, and context-free graph grammars determine one of these insertion Lie algebras, which is not necessarily the same as the one that actually occurs in quantum field theory, but has sort of the same structure. So from these kind of formal languages, you can produce insertion Lie algebra that look like the quantum field theory ones. And also, when you look at the Feynman graphs of a quantum field theory, they are a graph language. And there's a bit of a discrepancy in the sense that the Lie algebra is not of this kind, no, but they do form a graph language. And the thing is that these graph languages in general are not context free, though they are context sensitive in the appropriate sense for graph grammar. So the reason actually why these graph grammars exist is because the theory of formal languages, although was largely developed to try to understand generative linguistics and human languages, it actually turned out to be very useful in describing languages in computer science and in the theory of computation. And in particular, when you want to describe computations that have a lot of parallel computing involved, it's sometimes more convenient to use things that it takes care of some graph architecture of your computational system, and not just of the actual string of instructions, tape instructions on your automaton. And so this extension of formal languages was partly developed to deal with parallel computing problems. And this produces that they produce a language that consists of a family of graphs. And the production rules of the language, in the case of the formal languages that we've seen in the linguistic setting, they were designed to replace some non-terminals with some other string of non-terminals or string of terminals and non-terminals until you reach only terminal words, and you get the words of your language. And here, the production rules, they actually are designed to substitute certain parts of a graph with certain other graphs. And so they have this kind of insertion type property, insertion and gluing of graphs. And again, you have some initial graph as the start point rather than some initial non-terminal symbol. And again, the possibilities of keeping track of edge and vertex labels and labeling them by terminal and non-terminal symbols in the. So there's different formulations of these graph grammars, and they partly depend on the fact that there are two basic ways in which you can think of graphs as a combinatorial object. One of them is that you assign the set of vertices and you assign the set of edges as relations on the set of vertices. And so you give, if your graphs are directed, you give source and target for the edges. If they're not directly, you give the boundary of each edge. And the other way of thinking of graphs, which is more the one that occurs in quantum field theory, is that you think of them as a set of corollas with certain valencies, and then an involution that pairs the half edges of each corolla into edges. And this allows for also half edges that remain unpaired that form your external edges, and the ones that are paired form the internal edges. And so this is like there are these two dual ways, not dual, but sort of complementary ways of thinking about how you build graphs. And in the sense, as I said, the second one is sort of much more natural when you think in terms of quantum field theory, because that's how the Feynman graphs are assigned. You have the type of interactions, which are the corollas, and then what is interacting with what is the pairing of the alpha edges of the corollas. But I mean, depending on, you can take one or the other point of view, and then you define slightly differently how the production rules of the graph grammars are. But in general, so let's say that you think in terms of set of vertices and set of edges, then you have a non-terminals associated to edges and non-terminals associated to vertices. And you have some kind of n-terminals associated to edges and vertices. And some start graph and a finite set of production rules that tell you how you can modify parts of the graph that are marked as non-terminal into either other graphs that with non-terminal graph or into terminal structures. And the production rules in general are combining some kind of labeled graph, which is what you start with, your left-hand side of the production rule, and some other label graph, which is your what you'll end up with so it's like when you're moving from one state to another on your automaton, you move for a certain graph structure, and you want to replace it with another graph structure. And the way you do that is through some matching. So you want to have label preserving isomorphism between the thing that, a part of the thing that you want to, that you start with, and a part of the thing that you want to combine with it. So it's like saying that I take some substructure here and I glue it together with an identical substructure on the other side, and this allows me to combine two graphs into one. So it's again a bit like this insertion, rules that I described. You look everywhere in a certain graph for places where you can make this replacement, and then you do it in all the possible ways. And in this setting, what does it mean that a grammar is context-free? It means that the structure that you use to do the gluing is a single vertex. If it's something like a bigger structure, that's the context. That's the context that tells you when you can or cannot apply the given rule. And if one takes this definition of graph grammars, then there is an analog of the Chomsky hierarchy. It's slightly different from the way it works for the usual formal languages, but there's still a classification of the type of automata that can compute different classes of formal languages in the graph sense. And so there's a bunch of things, the various properties of graph grammars, and mostly there are applications to computer science, because that's where these are actually relevant. So, if one wants to compare this generative process in quantum field theory that is described in terms of Hopf algebras, as I did just now, and the formal languages point of view, there's a few comparison here and there you find in the literature in terms of describing the recursive construction of Feynman diagrams for certain theory, but there's basically two things which are the ones that I mentioned a moment ago. There are two ways in which these two points of view are related. One is the fact that if I give you a context-free graph grammar, then I can associate with an insertion algebra of the same kind as the ones that are used in quantum field theory. And this is simply the fact that I can construct a bracket in the same way that I did for the insertion at vertices. Here, the insertions are not, well, if it's context-free, they will really be insertions at vertices, but if they are more generally, they are insertion according to whatever is the structure. The point is that when they're context-sensitive, this bracket might or might not satisfy the right Jacobi identities. So that's why you're guaranteed that the construction will work if your graph grammar is context-free. Then it will really look like this insertion algebra. If it's context-sensitive, it might or might not work. And okay, let me just say that you get this kind of insertion pre-Lie structure, and you get the corresponding algebra that looks like it is insertion algebras of quantum field theory, although in general they're not the insertion algebra of some particular quantum field theory. But on the other hand, if you do start with the quantum field theory, you can construct a graph grammar. And the problem is that now you don't construct a context-free graph grammar. In general, you construct a so there's kind of these two ways are sort of not exactly matching in the middle. But for example, the way you do these graph grammars is basically building the Feynman graphs on the basis of what the basic propagators are for the fields that you have in the quantum field theory. And then the production rules tell you how to glue these together into the graphs. Like, for example, if you have just a phi-4 theory, then you have the fundamental interaction, which is this fourfold basic interaction term. And then you have two types of production rules. One that connects, tells you that you can connect edges of this, and one that tells you that you can close into loops. And these are basically the two types of forms that the involution that matches edges can have. One is that you match edges on the same corolla, and one that you match edges in two different corollas. And if you combine these two, you get all the possible Feynman graphs of the theory. So these are the only two production rules that you need to do that. And you can see the same, for example, if you have both phi cube and phi-4, you have again, slightly more, no possible production rules, but again, you have a finite number of production rules that start from these basic interaction terms and build all the possible Feynman graphs of the theory. And if you have, for example, the electrodynamics, where you have a scalar field and you have another kind of field, then you have two different kind of propagators. And then again, you have rules that involve the vertices coupled with the different type of propagators that again give you, the entire construction of all the possible Feynman graphs. So so I'll stop here with the quantum field theory part. And so you see that kind of everything has a corresponding parallel in this story. Now, next time I'll tell you a little bit about this intermediate step about going from the physics to the theory of computation with the same of algebra and the kind of renormalization idea. And I'll make the next step from that to returning to our setting in linguistics and how we can use all of these things there for trying to make syntax and semantic interact with each other.